Hi guys, the first thing we're going to do today will be an application of the implicit function theorem that we did last time. Okay, so let's review the implicit function theorem and then its application to dynamical systems in the context of perturbation theory. So how was it? It was something like this here. If we have a function defined on, let's say, a product of two open sets. This is in R and this is in Rn. Okay, so this function is class C1, meaning is continuous with the differentiable and with the derivative continuous. Okay, and to put it in the context of what we have to do, I said, okay, so epsilon is one-dimensional, x could be n-dimensional, and epsilon and x lands into an f of epsilon and x, which obviously is in Rn. All right, and then we have some special values, epsilon naught and x naught, which are in this domain, right? So maybe I should write this open, just to be precise a bit, okay? All right, and then we know that f in epsilon naught and x naught equals y naught, okay? And then we also have that the determinant of df, a dx, so the Jacobian, if you want, or the partial derivatives, right, with respect to x there, right? At this particular chosen point is non-zero. Well, then, this is the case, then we have a neighborhood of epsilon 0 and a neighborhood of x naught and a function g defined on u goes into v. So epsilon will go into a g of epsilon. And by the way, this is in Rn, yeah, okay. That is of class C1 as well, such that f in epsilon, g of epsilon will still be y naught, okay? And the picture that I did last time, and I remind you, right, it's a nice way to remember this theorem, is about persistence, as I was saying, for roots of equations, for equilibria in differential equations, which are essentially roots of equations, right? So it's a persistence of roots of equations. Okay, so here, if we have here a function that depends, right, parametrically of an epsilon. So let's say we have a class of functions f of epsilons and x, right? And here, this graph is the function drawn for epsilon naught as a value. And here we can see we have here the root of, let's say, epsilon, f of epsilon and x equals 0, right, in epsilon naught. So in this particular drawing, I'm choosing, okay, I'm going to put it y naught to be 0, okay? So I'm looking at this class of equations, all right? So here, this guy here, right, this fellow here is f of epsilon naught x naught equals 0, right? Okay, so the derivative there, if I do df dx at x equals x naught, is non-zero. Okay, so you see that the slope, right, is non-zero, right? So we have a nice tangent line, right, to the graph that is not horizontal, right? So this is this guy, all right? So now if I jiggle the function, if I do epsilon near epsilon 0, so I start, perturbing the epsilon value from epsilon naught to something, could be you know, quite close, right? Well, the thing is that, oh, I want to use a light green for you. Well, the thing is that this root, as we say, will persist, okay? So here it is. It is still there, right? This is the graph of y equals f of epsilon and x for, you know, epsilon near epsilon 0, let's say, and you can see that, you know, jiggling it, it's still there quite fine, right? So here it is. So that's the root of epsilon and g of epsilon if you want to go here. Okay. So there you go. That's what it says. Okay, the theorem, right? So in a way, you know, this root x naught, you know, persists as an x of epsilon. So I can call this g if you want. You know, I can kind of think of it as an x of epsilon. Actually, some people write it like this. And, but I don't want to confuse you in any way, so that's why I keep a different notation. So this being said, this is the review of it. Let's see how we apply it in a system, okay? So here is my example, right? So application to persistence of equilibria in ODEs with parameters. Okay, we'll have just one parameter. The technology, if you want, philosophy is the same, right? It will be a higher version of implicit function theorem that actually I want to do today. Okay, so here is this example. So we take an ODE, and I have it here worked out. Okay. Done. Done. Okay. All right. Good. So now we observe that if we take epsilon 0 and x naught is 0 and y naught is 0, right? So we have f in 0 and 0. Oh, I should say, what is that? Okay. So if we're looking for equilibria, right, we have to solve. Let's just take this out. Let's just do this out. So now we're going to apply this theorem to persistence of equilibria in ODEs with parameters, especially with one parameter. Okay, so application to persistence of equilibria of ODEs with parameters. Okay, so there you go. Example. Example. X dot equals x squared plus xy. So I have a system. And I did the calculation and everything. Okay. Plus x, and then y dot equal minus y plus y squared epsilon y plus x minus 1, right? So what are the equilibria of this system? Okay, so we do right hand side equals 0, yeah? Okay, so we have to solve x squared plus xy plus x equals 0 and minus y plus y squared plus epsilon y plus x minus 1 equals 0. Okay, so it's quite a system, isn't it? You know, I mean, I can try to do all kind of stuff, but Okay, the requirement is, okay, either equilibria, and actually what I want to show you is how, you know, an equilibrium that we can detect by eye, you know, in a particular case of epsilon, and that would be for epsilon equals 0, then, you know, that one will persist for small values of epsilon near 0. Okay, so for epsilon equals 0 and x and then, right, then we observe that x, let's put 0, y 0 equals 0, 0 is an equilibrium, right? Okay, so you can see it by eye. If you substitute there x and y with 0, when epsilon is 0, you just get 0. And actually, you can say for epsilon 0, so let's call this one epsilon 0. So we're in, you know, in line with the theorem as it was written, right? Okay, so now the question is, does this equilibrium persist for small values of epsilon? Small values of epsilon. Okay, just there. Okay, so to see if this is true or not, okay, what we have to do, we have to set up a function. So let's set up this function f r to R2 goes into R2. So it takes the epsilon, it takes x and y, and produces f in epsilon and x and y. On purpose, I'm putting them as paired, so you see how the theorem goes, you know, in kind of a organized way. So there's the upper part, right? And then, you know, down is minus y plus y squared plus epsilon y plus here x minus 1. So there you go, okay? And this function is class C1, yes, okay? So all differentiable, actually is analytic, to be honest, you know, so even if you differentiable one is domain, okay? And now what do we have to do? Okay, so we have that f in 0 and 0, 0 equals 0. Yes, okay. So that's exactly the statement of there is an equilibrium for epsilon 0. You know, x naught and y naught being 0, 0. Good. Okay, and now we have to do determinant of df, dxy. Okay. So this rank condition actually at 0 and then 0, 0. So we have to compute this thing. Okay. So what we have to do, we have to do determinant of, now I'm going to do the derivatives there, right? So this would be a 2x plus y. And then we have a plus 1. Okay, good. And then we have x. And then here we have here x. And then we have minus 1 plus 2y plus epsilon. Okay, so this is the derivative which has to be computed at 0, 0. Okay, so this will be determinant of, now when we plug in the numbers, we have 1, 0, 1, and minus 1, which turns out to be minus 1, which is non-zero. Okay, so then by the implicit function theorem, there is a neighborhood of 0, and there is a neighborhood of the pair of 0, 0. So one is for epsilon and the other one is for xy, right? And G defined on U goes to V. So an epsilon goes to a G of epsilon, which by the way, V is in R2, right? So this will be a G1 of epsilon and the G2 of epsilon, okay? Such that this G is of class C1 and essential, I have to squish it in the corner there. F of epsilon, G1 of epsilon, G2 of epsilon is 0. Okay, so let's try to squish it again. All right, I'll squish it here. Okay. So epsilon goes into G of epsilon, which has two components. G1 of epsilon, G2 of epsilon. Okay, and this is of class C1, so it's differentiable with the derivative continuous. Okay, such that F in epsilon, G of epsilon. Okay, so G1. G1 of epsilon and G2 of epsilon. Let's put the extra. Let's be 0, right? So in other words, the equilibrium persists. I will not write it separately, but that's the answer. Yes, the equilibrium persists. And this is because the implicit function theorem applies in this case. We have the rank condition that I'm going to write this one. What about this one? Okay, so I think it's clear how it functions. I don't see why it would be very difficult for you to apply it for any kind of systems, as long as you understand what you're doing. I mean, essentially is, splitting, this right-hand side of the ODE system or whatever it is into the epsilon part, and the part, is the unknowns, and then, verify that you have a root somewhere, and at that root, the determinant of df, dx, y, z, whatever are the unknowns, is non-zero, and then, this means that the equilibrium persists. Basically, is this picture, but this picture is for the case when we have the function, right, defined on some domain R, this D1 and D2. Let's, D1 plus D2 goes into R, right? So D1 is in R, that's the epsilon, and this one would be dx. So the picture is for the, if you want the case n equals 1, this general theorem. So I think it's clear, my example here, which is so silly, or the writing gets squished at the bottom. Okay, so this being said, now what I want to do, is to give you the statement of the implicit function theorem in a more general case, and then to apply to somehow a side note into this course. So you don't have any offering in a course in manifold theory, and even if you would have, I think this would be a good prerequisite for that, So in modeling, in applied math, in physics, in whatever, we do is this formalism we call math, right? There are conditions that constrain the motion, okay, that constrain whatever the dynamics we have there onto invariant sets, so the easiest way to imagine this would be like on surfaces, like on a sphere, right? So you have motion constraint on the sphere. So once you want to study motion constraints to one of the surfaces, you better know your surface, right? You better know what you're stepping on, right? So of course, being math, you need to define what's a surface for in a consistent way, right? So once you understand what the surface is, then you can talk about the tangent plane, you can talk about tangent vectors, you can have a different vision of the thing, or how this, if you have motion constraint on different surfaces, maybe they intersect, maybe don't intersect, in any case, there is a prerequisite to study dynamics well into understanding the geometry of the space, the topology of the space, right? And one of oops, steps forward is to define what the manifold is, right? So manifold is a surface. When I say a surface is already, you know, so it's one way to define what the manifold is in a very abstract way with no environment around. Whereas what I want to do today is something less fancy, is defining manifolds as submanifolds of an environment that is larger and it includes it. And this environment is a vector space. So really what I carry in my mind is the image of a surface, right? Here is a surface, if you want, all right? And this is embedded in our three-dimensional space. So I'll put X, Y, Z here, right? And here is a surface. So when I'm thinking in this way, I already see, oh, okay, so to every X, Y, it corresponds a height. So here is the height. So I had a little interruption. That's the story with doing recordings at home. Okay, so right. So what's a manifold, right? So I kept saying, you know, I was saying that to me the simplest way to understand this is really like a surface, a smooth surface. So we're talking about nice surfaces, right? They're nice, embedded in R3. So basically, when I'm thinking about a submanifold, I'm thinking of I could actually write this, you know, a submanifold, okay, let's say in R3, okay, is something that is like a smooth surface, okay, inside or embedded. You see, I avoid to say the words embedded because it means something in math, right? But in common language is like, okay, so swallowed, okay, smooth surface inside here. I'm gonna put inside the vector space R3. And on purpose, I'm putting, you know, these words, you know, it's superfluous to say vector space, but I want to put it in there because, you know, the idea of a submanifold of an Rn, that's exactly what it is. It's like a smooth surface, you know, of some dimension embedded in a bigger Rn. All right. So here, you know, like I was saying, well, what I imagine is really like a, you know, surface in R3. So to every XY in the horizontal plane, I'll have an exit, right, an output up there. So here, you know, this Z can be represented as a function of the entries X as Y with F to be at least of class C1, meaning, you know, is differentiable, right? Nice, you know, no corners with the derivative continuous, right? So, you know, I could think further, right, that this surface, right, this submanifold is something that, you know, can be represented locally as what? Okay, so as this this height thing, as the graph of a function that is smooth. Okay, so what is the graph of a function, by the way? Let's just put it into. Okay, so I'll come back here to can be, right? Can be represented, okay, as the what? So the graph of a function, but I have a problem first, you know, defining what is the graph of a function. Okay, so let f defined on the domain goes to some codomain, let's say Rn. The graph of f is, by definition, the set of pairs x, f of x, where x is in the domain. So this is really, you know, what we see here, this picture of mine is really nothing else but, you know, this guy. Yeah? is the graph of a function, right? Because every point here, so every x, y, z is really represented as a point where this is x and y, and the height is an f of x and y, right? So it's the graph of a function. So now what is a submanifold? You know, what is the smooth surface submanifold of R3? Oh, it's a set that can be represented locally as the graph of a function, as the graph of a function. And then I added the word locally. Okay, why do I need this word locally? Well, there are sets in R3, there are sets in R2 that are smooth, nice. I mean, we can see them. And the easiest example is the circle, right? So here I'm going to take a unit circle. I'm going to take a circle. Oh, okay, this problem. Let's try again. Okay, here is a circle. Nice. Okay, so this is a curve object, a curved object that it's smooth, is nice, right? However, if I want to represent it as a function, I will need more than one. Okay, so and not any function, but the graph of a function that is of class C1, right? Of a function, okay, of a C1 function. Let's put it there because that's essential, right? So this guarantees that this is, there are no corners, no sharpness, no sharp corners, or anything like that, okay? All right. So I'm coming back to the circle example, okay? So here is my unit circle, well, a circle, okay? So I can say this is the set of pairs xy for which x squared plus y squared equals 1, okay? So is this a submanifold of R2? Right? In principle, I can see that is a smooth surface embedded in R2, right? So it is a smooth, right, by eye, surface in R2, right? But then can I represent it, as the graph of a function all over, just one function? And the answer is let's try to do it, to see what the heck am I saying here that we cannot do. So if I take a point on the circle here, so let's take this point, right? So this is a point xy, right? Wherever, obviously I can say, oh, so y will be root of 1 minus x squared. Yes, absolutely true, right? But then there, to this entry x would correspond another point that is below, right? So this would be another point xy here, with x being minus root of 1 minus x squared. Okay, so maybe I should split this thing into the upper and the lower part. Absolutely correctly. All right, good. And there is even another issue, right? So is this derivative of this function? So for this case, x is, right, f of x will be, let's say f1 of x, and then this is x and then f2 of x, right? So this f1 and f2 of x, are they, nice and smooth everywhere, or, do they break somewhere? In any case, I know that this part should work for x positive, maybe 0. Okay, so I'll put here 0, right? Whereas this is for x negative. I won't put 0 as well because, well, it depends, right? I mean, yeah, okay, it can be 0, right? Okay. This is the unit circle, so it has some edge here to 1. It stops in 1 and then in -1. And then here, when we say x is, not x, what am I doing? Okay, so y is positive, right? So y is the upper part there. And y is here. Good. Okay, so I was saying I cannot put y in both sides, you know, y equals 0, because it's a kind of, you know, like, okay, so it should be just 1. And by the way, you know, this C1 condition, right, it shouldn't contain any sharp corners, so it better be defined on open sets, right? So C1 function locally, I should say here, on defined on open sets. This is quite delicate to do this right? I mean, we have to be careful. Okay, so maybe I should take the 0 out. Okay, so now they're open, but then it's what about at x equals 0, at y equals 0? What can we do, right? So maybe I should mark these points that we're taking them out, right? So this is y equals 0 on the circle. And these points are not caught by any of these functions that I just defined, right? Okay. So another issue would be for this circle example that if I do f1 prime of x, right? So now I can take these ones out, right? So if I do f1 prime of the derivative, right? This we end up with minus x over root of 1 minus x squared, which is lovely up to x equals 1. So this really has to take out the points plus and minus 1 because there we have 1 over 0, so we're done, right? So this f1 actually, y equals 0, I wanted to say. So this f1 is defined only on minus 1 to 1 goes to r, right? Okay. What about f2? Well, it will be the same thing, right? So if we do f2 prime of x, this is x over root of 1 minus x squared. Again, you know, the same issue, x cannot be plus or minus 1. So this f2 better be defined again on minus 1, 1 goes to r, right? Okay. So locally, for now, right, we are okay in seeing as the graph of a smooth function or C1 function, the upper part of the circle and the lower part of the circle. And we have issues with those endpoints, right? So here is where it comes, you know, this thing with the local part, right? So now we're gonna catch these red endpoints as see them as the graph of a function, right? Where they will be inside of the graph of a function that is defined kind of the other way around, so they show up as as they should. Okay, so in this case, what I'm gonna do, I'm gonna say, look, I'm gonna do it the other way around. Here is an y, and I'm gonna consider the y as an entry, and I'm gonna put the x here to be the right. So this would be, okay, let's do it the other one. So it's an x and y as a point, right? Which I will see actually as, okay, maybe I should, okay, try to do it this guy, right? So this would be, so it's on the positive side. So it's root of 1 minus y squared and y, right? So here, this point is actually the outcome of a function, right, that has entries the y's and produces the x. And in this way, right, we see that even this point here, you know, this x equals 1 is caught by this particular function, because, you know, when y is 0, right, x is 1. It's okay, right? So in this case, we will have, right, so I'll have another point here, right? So this one will be minus root of 1 minus y squared and y, right? And I will have a pair of two other functions that are doing this job, okay? So this would be an f3 of y, okay? And this would be an f4 of y. And I won't write the domain and whatever, but where do they lose their nice properties. Okay, so when we do the derivative, we'll see that that one blows up where? Oh, again at these edge points. I'll do them with gray. One here, or maybe I should do them with, and one here, right? So for these edge points, right, the domain, if you want in Y, doesn't catch the other two edge points. So indeed, the circle is a smooth surface inside R2 because it can be represented locally as a graph of C1 function, right? So in this case, we need 4 functions to do it, right? We defined F1, F2, right? So it's the root up, the root down. This one, you know, loses the edges x plus and minus 1 because there the derivative doesn't exist, okay? So I cannot do that, all right? As I cannot take as a whole function to be the entire circle because that's not a function, right? You know, to an entry of x, you should have just y and not 2 y's. All right. But now what do we do is this edge is x plus and minus 1. Oh, I'm going to flip the entry, right? I'm going to say, oh, the entry now is y. And I'm going to produce the x, you know, with the root of 1 minus y squared. And of course, now I'm going to have 2 sides the other way around. I'll have, you know, so for you would be left, right? And the right side, right? You know, which of course, when we express as functions, they're beautiful, except for the edges y and plus and minus 1, right? So there you go. The circle, by intuition, is a smooth curve in R2. But how we express this mathematically, how do we do this mathematically, is a completely different story. And it's more complicated, but I don't think it's super complicated. Okay, so once we get the idea with the circle, I think we can just fly to a sphere. We can do all kind of other surfaces. But now would be the time to see how the implicit function theorem is related to this thing and what that one, you know, how that one gets to apply to this kind of problems, right? Okay, so now I'm going to write the definition of a submanifold in a smooth submanifold of Rn in its full glory, and then we'll try to fit the definition on this intuitive thingies that we wrote here, okay? So, well, okay, not okay. I have this thing saying okay all the time. Okay, so let's, okay, definition, all right, definition. So let this, okay. So let k and n be 2 natural numbers. 0, let the k less than n. A set M inclusive in Rn, okay, is, well, it cannot be equal, okay, is, okay, and actually this set, you know, we should say that is a non-void set, just in case, okay, let's just non-void, let's be precise, okay, over Rn is a k-dimensional submanifold of Rn if for any point, let's say z, not z, but any point x, I'm going to make it like a vector in M, okay. There is a neighborhood, so let's say x, no. There is a neighborhood U of this x vector. So on purpose, I'm going to say, you know, I'm calling it with x not because I see it as a vector in Rn, okay? So I know that it's on M, it's right here. It is on this M, right? But it's still part of the bigger R3 space, right? Okay, so there is a neighborhood in there. So let's say U in M, okay? So it's in there. Okay, and a function f defined on U goes to Rn minus k of class C1. So again, you know, is the smoothness best, okay, such that for any, U can be seen as the pre-image of 0 of this function, okay? Well, actually, it's not correct to say this because we want you to be an, I would prefer to write it like that, such that, I know, okay, such that for any x in U, we have f of x equals 0, and here's the rank condition, rank of the matrix formed by the derivative of f with respect to x, okay, this rank will be n minus k, okay, for any x in U. Oh, it looks very complicated, doesn't it? But, let's try to fit it on this example here up here, okay? So for this example, right, I would, we had k is 2, n is 3, so n minus k would be 1, so that m, I would think, you know, it's a two-dimensional. Intuitively, I'm saying it's a two-dimensional submanifold of R3 because, you know, it's a surface. At any point on the surface, I would have two independent directions to walk on. Well, by independent directions, understanding, well, at the point of the surface, I will take the tangent plane, so something that kind of touches there, you know, and it's flat, and then, you know, in the tangent plane, it's two-dimensional, so I'll have two linearly independent vectors, right? Tangent plane will have dimension 2. So that's why I kind of say, you know, I expect that this one is dimension 2. So, let's see. So here I would have a picture that, okay, let's make that M. Okay. And let's put it in R3. So that would be the Z. Okay. Oh, no, that's one. One. Okay, so that's my M there, that's set. And let's see if we can fit the definition, right? So any point in M, you see, that's why I put that vector thing, because here, right, if we take an X naught here, this actually coincides with an X0, Y0, Z0, right? So it's any point I take here. Let's put it here. That's it here. So this wonderful point. I'm trying to make a nice picture for you guys. Very suggestive. So this guy here is X naught, Y naught, Z naught. So is that X naught, eh? Okay. So any point in M has a neighborhood. Okay, I have to make like a patchy thingy, right? So it's neighborhood. Well, it's nice and round. This neighborhood doesn't have to be in any way. Yes, my pictures. Oh, I have a thing making it as a corner, but I don't want a corner. Oh, so take it. It's smooth, yeah. It's a patch on that thing on M. Okay, that's the point X naught. All right, so here we have this U. There's the U, okay. All right, so I did that thing, that U, such that for any X in U, I'm gonna make an X with red. Okay, so here. So that's an X y, z, which is actually, you know, any x in z is like an x from the theorem, from the definition, right? So for any x in u, I'm going to put back mine. Okay. There is a function, right? There is a function defined on u, right? So that this thing, right, for any x in u, this f of x equals 0. But the function goes on from u to Rn minus k, right? So there is a function defined on u, goes to Rn minus k. In this case, n minus k is 1, okay? Such that for any x in u, so for any x, y, z in u, right? Right, f in x, y, z equals 0, okay? Okay, so what could be this f of x, y, z in this case? Well, I think that this guy here would be a function given by the height, right? So the entries would be the x and y down here. Well, I should put it under that red dot, right? So the entries would be the, somewhere here, right? So this would be the entries x and y, and then the output would be the z, right? So let's call this function z equals h of x and y, h from height. So z is the height at x and y, okay? So just to not call it f because I already have taken, right? So this f actually can be seen as the h in x and y, so the height minus z equals 0, right? So for any x, y, z, indeed, I can see this point as the level set 0 of this function. So if we have let f of x, y, z to be, right, h of x, y, the height in x, y minus z, indeed, right? Okay, that's right, nicely. Then indeed, okay, any x, y, z in u, right? And actually on the entire thingy, because you know that thing, okay? Okay, for any x, y, z, you know, we have f of this x, y, z equals 0, right? And there is one more thing to verify. So what is the rank, right, of df? And then they say dx, right? So in this case, right, we would have to do rank of, so for us would be this, right? So this is, the function is, goes to R, right? So we have to do df dx, df dy, df dz, right? So in this case, we should verify the rank of dh dx, dh dy, and then we'll have a minus 1. So the rank of this should be 1, which actually cannot be anything but 0 or 1, because this guy, but actually is 1, because the rank, if you remember, right, is the number of linearly independent columns. And in this case, right, that can be just 1. Oh, I see. Okay, right. So the issue is that right, we have to write this as a linearly independent rows or columns, right, as the transpose, and then this way actually can match it to your knowledge of linearly independent, number of linearly independent columns. So in this case, for number of linearly independent rows, you know, if you take it as a row, right, it's just, you don't need this transpose. If you want to take it as a column, you know, put it as a transpose, right? I don't think this is the issue. The rank of a vector can be 0 if all the entries is 0 or 1, okay? Because you just have one row or one column. So in this case, we see that this is 1, so it's non-zero, right? So for this expression. Yay! So somehow, indeed, right, we can match this definition of ours. It's not ours. Someone did it, right? Thought about it properly, with the intuition that a submanifold is a smooth surface embedded in a bigger space. Okay. And practically what it means that at any point can be expressed, at any point on that set that we call submanifold can be expressed as a graph of a function, right? So we had this example with the wonderful circle, and now we have the definition. So now what I want to do, I actually want to match the implicit function theorem with this thing, okay? So let's see if we can do that, okay? So the first thing I want to do, I know I'm terrorizing you, is a little bit of more upper level math, if you want, you know, less calculation, a little bit more thinking and definitions and whatever. Okay. So what we need now to do, what I will do, is to write the implicit function theorem in a more general case, okay? So it's really like the other one, it's just that instead of epsilon, we'll have like a higher dimensional epsilon. So maybe, actually, I will write it with epsilon like being an epsilon vector, but, or not, okay? The implicit function theorem, more general case, okay? So it's like this. So let's say we have some natural numbers, okay, in order, okay? And then we have D1 in RK, D2 in, could be equal Rn. They're both open sets. That's right, nice. Open sets. And then we have a function f defined on D1 cross D2 goes into D2, into, not D2, into Rn. That's what I meant. So this guy, right? So this is in RK and this is in Rn. You see the pattern here? Okay, so the dimension of this fellow is the same with the dimension of the codomain. Okay, all right. So now this takes an x and the y. I was just about to write an epsilon, and produces an f of x and y. Good. All right. So now we're going to have 2 points. Okay. Such that, let's say, f in x naught and y naught equals 0. Okay. And then we also have that if we do the determinant, I tell you, it's exactly like the other one. The difference is that, you know, the first entry is not one dimensional, it could be k dimensional. df dx, okay, this x naught, y naught is non-zero. Okay. Then, so that was the hypothesis. Then there is a neighborhood u of x naught and a neighborhood of y naught and g, a function that goes from u, lands in v, so it takes an x and produces a g of x, okay, which is in v, which is in Rn, okay, just to make sure that we know our dimensions, okay, such that for any x in u, I'll write that, f in x and g of x will still be 0 for any x in U. Huh? So it is exactly like the other one, okay? And then the proof is, if you remember, you know, we did the proof for k is 1 and n is 2, right? And I was saying, okay, this is like, you know, really easy to understand, but the ideas are the same when you go to higher dimensions. Okay. So now let's see what this one has to do with submanifolds and how, you know, it gets into action. So for this thing, I have the example of a sphere, right? Which is terribly, it's not complex, it's just, people don't really like to, it's not that they don't like to write it. It's hard to write, hard to kind of explain, but actually it's not terribly hard to understand, you know? So it's like the circle thing. So here with the circle, you know, what was the key, right? Was the key that locally, right, we have to express any point on the circle as the image of a function, right? So that point becomes part of the graph of a function that, you know, at least is defined locally, right? So that's exactly what will be with the sphere. The thing is that we cannot have just one function that would express the entire circle as the graph of a function, right? So that's why we had to have quite a few of them. We had 4, right? So, you know, because we had 2, you know, for the upper part of the circle, the lower part of the circle, and then the edges were left out. And then we need a couple more for those edges to cover those edges. But this couple more, okay, they were undefined at the north and south pole. So actually, it's the same thing with the sphere, right? Just that the dimensions will be higher, right? And then we'll see where this one gets into action. I guess I could put it into action here, but, you know, it's a little bit too low dimensional for my taste. Okay, so the following are equivalent. Okay. M is a k-dimensional submanifold, smooth, let's put it smooth, smooth submanifold of Rn, and whatever x naught in M no, I'll put it in nice words, okay? M can be represented locally as the graph of a function. Okay, so the implicit function theorem allows us to apply this statement directly and beautifully, whereas for this one, this is a longer road. Okay, and so this is with I'm going to call them patches. Okay, see the circle example, whereas this one, okay, this is with the implicit function theorem. Okay, and see the sphere as to example. So let's write like this. Let's prove that the set, okay, so this is the set X, Y, Z, for which, so I'm taking the unit sphere, is a 2-dimensional smooth submanifold of R3. Okay. By the way, I defined this submanifold. There is some manifolds that are not smooth. Okay, so it's like piecewise smooth or something. So when I say submanifold in our context here, for the this first time that you see them, hello, bonjour. Let's take the smooth. Okay, they're smooth. All right. So let's see if we can match. So of course, we could think about the sphere. I'm gonna make here a nice sphere for you guys. We could try to prove that is a submanifold, just doing what we did with the circle, like for every for every point on the sphere, try to find the function and make it locally as the graph of a function. Actually, there is a theorem that proves that, the definition that we wrote is equivalent to saying that any point on this set that is a submanifold is actually can be represented locally as a graph of a function. Okay, so these two things are equivalent. We are not doing the equivalence here or the proof. Okay, it's just I'm telling you. So what I'm trying to tell you is that, is now I want to apply the implicit function theorem in proving that this is a submanifold of R3, rather than doing the thing that every point on the sphere is locally the graph of a function, which actually you can see it will be the same idea as at the circle, right? So for the circle, we had the upper part, we had the lower part, each one graph of a function, the edges were left out. So now for the edges, I'm going to do functions for which the entries are at the vertical, if you want points on the vertical, and the output is, on the west side or whatever side is for you guys. So for me, is this west side, So all right, so it's left hand side and right hand side. Okay. Now for the sphere, right, we would need. So you have the height function for the top part, the height function for the bottom part, and then you have the equator left out of the business, and that's exactly where these functions would crack. They cannot do the right thing. The derivatives there will just blow up, right? The rank condition, if you want, won't be fulfilled. So then you have to cover the equator with patches, with functions that are coming, from the lateral side. So, the entry will be something, a point on the vertical plane, and then it will give you, values. The outputs would be on this side hemisphere. And then you still have 2 points left out, and for that one you'll need to have another half spheres represented as graphs of functions. So the total of 6. All right, kind of hard to work out, right, and to write all this stuff. So here comes this thing where we can just implement the implicit function theorem with, right, where is it? Okay, so I messed up my my pictures here. That doesn't matter. Okay, so let's see. Okay, so the definition would say, this definition would say that for any point on the sphere, if I could represent, I could find a function for which that point is the level 0. And we have a rank condition. That would be the key. Okay. So let's see. So let X, Y, Z be on the set. Let's call it S2. Okay, on S2. So that's an X, Y, Z. And I'm going to propose your function F, and F defined on can be anywhere, right? For any, okay. And U, V of Let's put the 0 here. Okay, so it can be anywhere, right? X, Y, Z, P of X naught, Y naught, Z naught. So F defined on U goes to Rn minus K, right? So in this case, K is 2, N is 3, N minus K would be 1. So it has to land in R, right? So we have X, Y, Z goes into F of X and Y and Z. And this one, I better make sure that F of X, the sphere becomes, you know, S2 becomes the set of X, Y, Z for which F of X, Y, Z equals 0. Oh, so what would be this one? Ooh, ooh, of course, right? Obviously, my set as defined here coincides with the level set 0 of this function. Okay, so what it is to verify left? The rank condition. So let's look at rank of df dx, y, z. There you go. Okay. But this x naught, y naught, z, right? Okay. So what do? We do df dx, df dy. So this would be rank of df dx, df dy, df dz. Okay. But x naught, y naught, z naught. Okay, so this is rank of, okay, this row matrix 2x, 2y, 2z, right? At x naught, y naught, z naught, which is 2x naught, 2y naught, 2z naught. Now, this rank will never be 0. So I repeat, this is a one row matrix. So the rank can be 0 or 1, right? But the rank is 0 when all the entries will be 0. But this is not possible because these guys, right? So when we add these fellows, we have to get 1 because that's how the set S2, this S2 was defined. So if they're X naught, Y naught, and Z naught, the 3 of them 0, you add the square of them, you get 1. No, it's not possible. So at least one of them is non-zero. At least one of these X naught, Y naught, or Z naught is non-zero. So it's really, you know, it's like you're on the sphere, right? So if you're on the sphere, you cannot be in the center. Huh? Okay. So this is, the rank will be 1. So indeed, okay, so S2 is a two-dimensional submanifold. Again, I'm writing this here, of R2. Of R2. How do I manage, huh? Okay. That's the thing, I don't manage. Huh? Okay, so this thing, so whenever we take, you know, an X naught here, here's the X naught, Y naught, Z naught, right? We don't have to go through the pain of that that wonderful maps.